In this video, we are going to solve some problems in general organic chemistry. Give the product and show the mechanism for the reaction below, and indicate the stereochemistry of the resulting product. Ethene plus bromine gas in the presence of light. So this is the halohydrin reaction. Now, let's write it here. So the starting product is an ethene. Then we are doing it in the presence of bromine gas. And then we have light here. So the product is going to be a trans product. The stereochemistry, this is a clear example of halohydrin reaction. So this is the product we are going to get. We are going to get a CH to CH2. However, we are going to get one bromine here and then the other bromine in this place. So a clear example of halohydrin reaction. So the stereochemistry is a trans product. Now let's show the mechanism for this reaction. So what happens is that this ethene is a nucleophile and we have the bromine gas in solution. So with the lone pair of electrons, it will attract bromine. However, bromine has 3 pairs of lone pairs. So when it attracts bromine, this bromine in turn will attack this carbon, and then that will cause this bromine atom to leave. So in the next step, we are going to form the cyclic brominium intermediate. So it's going to be CH2, then single bond CH2, then the bromine is here. So this is the cyclic brominium intermediate. Then the next step, what we are going to do is that since we threw off Br minus, remember it's a nucleophile, so it's going to attack one of the carbons and making these electrons to be moved to this bromine, and therefore we are going to form the trans product, which is the CH2, but this one is at the opposite side, which is this, and then this one too is at the opposite side. So bromine is here. So 1,2-dibromoethane. If we come to the second part, it says that deduce the degree of unsaturation in C5H8NSBr. So degree of unsaturation is giving us 2 times the number of carbons minus the number of protons plus the number of nitrogens minus X, where X is the number of halogens. All of that divided by 2. So this is equal to, there are 5 carbons, so 2 times 5. Then there are 8 hydrogens, so minus 8. And the number of nitrogens are 1, so plus 1. And the number of halogens is 1, because there's only Br here, so minus 1. But sulfur does not come into this. Sulfur and oxygen are all the same, so divided by 2. So plus 1 minus 1 can cancel out. 2 times 5 is 10 minus 8 divided by 2. Sorry, I made a mistake. There is plus 2 here, so there's supposed to be a plus 2 here, and therefore minus 8 plus 2 will give us minus 6, and 10 minus 6 is 4, so this is equal to 4 divided by 2. 4 divided by 2 is 2. So the degree of unsaturation in this molecule is 2. This problem is a problem in qualitative analysis. A student has 4 test tubes containing hydrocarbons labeled ABCD. After performing some simple experiments, a student observed the following. For each of the following observation, make inference. A. Compounds A, B, C decolorized bromine gas in the presence of tetrachloromethane, but D did not. Now, it is only alkenes and alkynes that decolorizes bromine gas in tetrachloromethane. So, it means that A, B, and C could be either an alkene or an alkyne. Either an alkene or alkyne. But D is neither an alkene or an alkyne. D is an alkene. Alkenes remain the same. Sorry, the color of bromine gas in tetrachloromethane remains the same in the presence of alkenes. So we know that D is an alkene. Now, when we come to B, it says that compound A and B reacted with hydrogen gas in the presence of Lindlar's catalyst, but D and C did not. Now, alkenes and alkenes do not react with Lindlar's catalyst. Lindlar's catalyst, it's only alkynes that react with Lindlar's catalyst. And therefore, A, let me write it here, A and then B are alkynes. But remember that we have already established that ABC is either an alkyne or alkene. So since A and B are alkynes, then it means that C is an alkene. And then we already established that D is an alkene. Now let's come to C. Only compound A produce white solid precipitate with Tollens reagent. What is Tollens reagent? Tollens reagent is used to distinguish between internal alkynes and terminal alkynes. So if only compound A produce a white solid precipitate with Tollens reagent, it means that compound A is a terminal alkyne. And then compound B is an internal alkyne. But alkenes and alkenes do not produce any precipitate with Tollens reagent. And this is also known as the silver mirror test. Now, if we continue, he says that if all the hydrocarbons contain 4 carbons each, then suggest a structure for the compounds. So since they contain all 4 carbons, it means that we established that D is an alkene. So that means that compound D is a butane. It contains 4 carbons. And then we also established that C is an alkene. So it means that compound C is 2-butene. And then we have also established that compound A is a terminal alkyne and compound B is an internal alkyne. So compound B is internal alkyne. So that is 2-butyne. And then compound A is a terminal alkyne. So A is 1-butyne. So these are the molecules that we are dealing with. A is 1-butyne, B is 2-butyne, C is 2-butene, and then D is butane. So we have this molecule and we are supposed to supply either the reagents or the final product for the various reactions. So if we start from the top, so this molecule is 1-propyne. Now, if you put in hydrogen gas in platinum in a propyne, you convert it to the corresponding alkene. So in this case, it's going to give us a propane. So this is the molecule we will produce. Now, this is hydration of alkynes. When you do a hydration of alkyne, You can see that this water in H2SO4 and then mercury sulfate. Hydration of alkynes is Markovnikov's reaction. It follows the Markovnikov's rule, and therefore we are going to produce a secondary alcohol. So this one is going to be 2-propanol. Sorry. So we are going to produce the alkenol first. And then what happens is that this alkenol will undergo tautomerization to give the corresponding alkanone. So the tautomerization will lead to this propanol as the final product. So if you come to this side, it is 2 moles of hydrogen bromide in the presence of a peroxide. So this is the halogenation of alkynes. But since we can see peroxide here, then it is anti-Markovnikov or the Karas effect. So this is going to form the anti-Markovnikov's product. And therefore, the bromine will be on the primary carbon. However, since there are 2 moles of hydrogen bromide, then at the end of the day, all the pi electrons will get used up. So we have protons here. So this is the product that we will form. Then here, we are moving from 1 propane to 1, 2, 3, 4, 5, 6, 7. So we are moving from 1 propane to 2 heptane. Now, you see that what we must first do, there is a proton here. So we need to use a strong base to remove this proton, because you can see that we have increased the chain. So chain elongation. So we need a strong base like sodium amide to remove this proton first. Then we will add the corresponding number of alkenes, haloalkene. So we are moving from 3 members to 7. So that means we are adding 4 carbons. And since there are 4 carbons, we need to add 1 chlorobutane. So you can see that this is 1 chlorobutane. 1, 2, 3, 4. So if the sodium amide remove this proton, then the 1 chlorobutane will add on to this side. So if we add on to this side, it will lead us to this molecule. Now, an alkyne in the presence of a limitless catalyst is going to give a cis product. So we are going to convert this to a cis alkene. So let's draw the structure of the cis alkene. So it will look like this. So this is the cis alkene we are going to form. Now, if we have a trans alkene here, it means that the reagent that was used is sodium in liquid ammonia. That is the reagent that gives a trans alkene. Sorry, so there is a pi bond here. Then now, if we put this molecule in hydrogen bromide, this is going to follow the Markovnikov's addition. However, you can see that this is a tertiary carbon, and this one too is also a tertiary carbon. So there are 2 possibilities. The bromine can go to this side and the proton go to this place, or the proton can come here and the bromine can come here. So there is going to be 2 different products that will be formed. So let me draw those products here. We are going to get this kind of product. 1, 2, 3, 4, 5, 6, 7, or 1, 2, 3, 4, 5, 6, 7. Or the bromine can be here. Now, in these 2 instances, you can see that this is 2 bromoheptane and this is 3 bromoheptane. They are different products. So these are the 2 products that can form. Then this one, in the presence of bromine gas, we are going to form This is a halohydrin reaction. So we are going to form a trans product here. And therefore, let me draw 1, 2, 3, 4, 5, 6, 7. So we are going to get this kind of product here, a trans product. So this is how the reaction will go. Complete the reactions below. Ethane plus iodine gas in the presence of heat. Now you see that this is primary carbon and this one too is also primary carbon. So it's only one product we are going to form. We are going to form CH3, CH2, and then iodine, then plus hydrogen iodide. But if we check this case, when we come here, mention four importance of organochlorines. The first thing is organochlorines are used as cleaning agents. So they are used for cleaning. And then the second one is organochlorines are also used for anesthetics. And then the third one is they are used for insecticides. And then the last one, the fourth one is organochlorines are used as refrigerants. And let's come to the B. What are freons? And give three commercial uses of freons. Freons are the fluorinated hydrocarbons. For example, CCl2F2. CCl2F2. This is a clear example of a freon. Or CHCl2F. This is also a freon. And then freons are used for one, propellant. Then the second thing is they are also used for refrigerant. Used as refrigerant. And then the last one is freons are used in aerosol insecticides. Let's come to the C part. The octane number of a certain fuel is 96%. Explain. So it means that we have isooctane. That is the good fuel. And then we have heptane. Heptane is the bad fuel. So if the octane number is 96%, it means that the fuel is 96% isooctane and then 4% heptane. But give four fuel additives that can be used to increase the octane number of petrol. The first one is the tetraethyl lead. And then the second one is ethanol. The third one that we can use is toluene. Toluene can also be used to increase the octane number of petrol. Then the fourth one is 2-methyl propanol. Then we may add the fifth one. Another one we can use is methylamine. So methylamine can also be used to increase the octane number of petrol.